Hello. A couple days ago, I recorded a video in which I solved problem 16, which is arguably the most difficult problem in this advent of code. We check the stats. Day 16 is like the day when we lost half of the programmers, of the solvers from the day before. So 16 was definitely the difficult day this year. So I solved this problem to the point to get the both gold stars during my video. It took more than 3 hours, but I was not happy with the solution I found. First, because I didn't think that the solution I found was really exploring all of the possible solution space. So let me show you what I ended up doing for this, how I ended up solving this problem or refactoring this problem to get the real solution, what in my opinion is the real solution, and a pretty fast one. So in less than 12 or 15 seconds, we get the solution. So if you remember this problem and you check the input, we have this kind of graph of valves. Each valve has a flow rate. So let's say valve EF, or this valve, can release 12 units of pressure every minute, and it is connected to all of these valves. So what I did is, first of all, I read the input, or we could run this code and see what happens. So this is the output of this code. Okay, it's a list of numbers. What are these numbers? Let's see. We are reading each row in which we get the valve, the flow, and the neighbors of its valve, and we store this. So we store the flow, we store the neighbors. Then what I'm going to do is I'm going to create a dictionary of the distances from each valve from one to another. Why is this useful? Because we see that all of these valves that have flow rate 0, we don't really want to be in them, and we don't really want to open them. It will take us 1 unit of time to open them, but this is something that will not give us any benefit. So what I wanted to do is I wanted to remove all of these valves from the graph. So I'm building a graph where we will have the distance from each valve to each other, but excluding all of this. So basically, the distance from here to each of its neighbors is 1. But if RC to QK, which I don't know where it is, but if this one has flow 0, and then you can go to another one that has a positive flow, then we want to update this to connecting this one and the other one with a distance of 2. So what I did is, first I created this distances dictionary in which I set a distance of 1 if the nodes are neighbors, or else 0 if they are the same node. So distance from one node to itself is 0, and 1000 otherwise. So 1000 is like my kind of infinity in this case. What I then did is I ran the Floyd algorithm. The Floyd algorithm, if you don't know, is a very simple algorithm of cubic execution time in terms of the number of nodes. Which does is it computes the shortest distance for each pair of nodes. So after running the Floyd algorithm, we have the distance for each pair of nodes. What we do now is we generate a graph for all the valves that have positive flow. So what we do is we filter the valves if the flow is positive, or if it is AA, because AA, even if AA has rate 0, we start there, so we want to add it to our graph, and we generate the graph. The last thing I do is I print the graph. So this graph, first I print the list, the number of elements, then I print the flow for each of these valves, and then I print the matrix, the distance matrix. So what is this? Here it says we have 16 valves. The first one has flow 0. This is the AA. And these are the rest of the valves that have some kind of flow. As you can see, the numbers match. So this is 12, 20. We must have some valve here that has flow 20, 18, and so on. So these are the flows, and these are the distances. From valve 0 to 0, and from 1 to 1, and from 2 to 2, this is the diagonal of zeros. The identity, so from the distance to oneself is always 0, and then we have the distance to all of the other valves. Now, what do I do this, or what do I use this input for? Well, I use it to as an input to the C++ program so if we run this this Python code, it generates an input. Let's call it in. And if I compile this program and I send the in, let's time it, and we get the solutions. So the solutions are 202020, which is the solution of the first part, 2320, and the solution for the second part, 2967. And the execution time is 14 seconds. So what does this C++ code do? That's what I wanted to show you in this video. So we have used Python to just modify, read the input, which is very handy. Python is very handy for this. And now we have this C++ code. I will go through this code a bit. I will maybe close this window and make this code bigger so we can read the code very clearly. First sum includes an order map and vector, which we're going to use. This is for simplifying the function calls. And now we have these three global variables: n, the number of valves; flow, the flow for each valve; the distances matrix. This is very simple. And the main, what it does is mostly it reads it. So we read the number of nodes or valves, we update the size of the flow, and we read each of these elements for the flow. And then we resize the vector of distances, we do it again for each vector, and then we read the distances. So now here we're just reading the graph. And then we solve the problem. Solving the problems means starting from having 30 minutes left from position 0, 0, 0. Let me see what this means. And opened 0, so we have not opened any valve, and we start in valve 0. And for problem 2, what we're doing is we have 2 visitors of the graph. So we have yourself and the elephant. That's what the statement says. I recommend you read the statement if you have no clue what I'm talking about. So what we have here is we have both agents, so yourself and the elephant, starting from position 0. Position 0, we have not opened anyone, and we have 26 minutes left. So let's start with the first part. So in the first part, what we are going to do is we will use what is called usually dynamic programming or memoization, in which you remember the results of the previous calls so you don't repeat them. What we're doing is we have this recursive call in which we have the time you have left, the valve you're in, and the valve that you have opened. This integer is a bit mask where we have a 1 for each valve that we have opened in the past. First thing, so if the time is negative or 0 or we have already opened this valve, we return 0. So there's nothing to do here. If time has passed, if we have already opened this valve, we cannot get anything else from here. Then we get this ID, and this is the memoization part. So this ID is just a mask of both the opened, the time, and the valve. So if you have already been in this valve, given this time, with this remaining time, and with the same valves that have been already opened, you have already explored this solution, then you just return whatever you computed in the past. So you compute this ID, this is a bit mask, we are shifting this opened and time, and we are ORing the 3 values, and we find this ID in the mem unordered map, and we return if the finding is different to the end, which means that it was found, then we return the value. So this is the memoization step. So this is like the end condition, the memoization step, and now we get to the logic of the problem. So initially, by default, you return 0. So for each neighbor, and we start on 1 because the 0 is the AA valve that we start from, and we don't ever want to travel to it because it has flow 0. So if we are in valve 0, which is the first case, in this case, we don't want to open this valve. So because it has flow 0. So what we need to do is we have to do the maximum for each neighbor between the return value, so what we have already found, and this recursive call. So we for each neighbor, we remove from the time the distance, which is the time it takes to travel to this node. Then the I, which is the neighbor we are visiting, and the opened. So we don't even need to mark the first valve as opened. So we just, if we are in valve 0, we just visit all of the other valves, which whatever distance it takes, and see and get the maximum. If we're not on valve 0 and we have traveled to this valve, this is a key insight we need to use. We have to open it because otherwise we would not have traveled to it. So we are only moving to valves to open them. Otherwise, it makes no sense to move to them. This is a way of making the search space slower. It doesn't make any sense to just go traveling to many valves, not opening any. This is kind of doing a simulation instead of an exploration of all the solutions. So what we do again is we do the maximum for the return value. Now, t-1, because it takes 1 minute to open the valve, so it will generate flow for one less minute, and after 1 minute, it will generate this flow for every minute. So this is the flow, the total flow it will generate for the remaining of the time. The flow this valve has multiplied by the time -1. And then we do a recursive call in which we, again, remove 1 from the valve because it took 1 minute to open it, remove the distance it took to go to this new neighbor, we go to this neighbor, and we OR the opened. So now we have marked this valve V as opened. To do it, we do this OR. This is the recursive calls that we do, and finally, we return the result. The important thing is that when we do the recursive call, the t is always smaller. The distance is always larger than 0, so the t is strictly smaller. So it cannot happen that we end up in the same function call before we save the result. So this is strictly decreasing. The time is strictly decreasing here and here. The I is changing, of course, and the opened is also always being modified, especially in this case, not in this case, but this is just the initial case. So what this makes sure is that we don't have any kind of cycle in our calls, so this will not hit an infinite loop, and then in the end, we save this number. If later in the search from somewhere else, we visit this same node with the same given time and the same opened valves, we will just return what we got. Now, part 2 is very similar, but it has a couple caveats. So in the part 2, we have 2 agents. It's yourself and the elephant. So how do we handle this? Well, we have 2 times, so time A and time B. So it's the agent, we call it A and B. Agent A is in this valve, agent B is in this valve, and they have this time remaining, time A, time B. And this opened is well, in this case, this is a uint. I think we need it in this case because we need to shift this more to the left, and then we would overflow with it. So what do we do? First of all, if we are exploring, we want to explore it always on the right, on the same order. So we are going to make the time A always larger. So it has some kind of logical sense in which you want to explore first the agent. So you want to decide where to move the agent that has more time. This just reduces the search space a little bit and makes the solution faster. So if time A is smaller, we just swap time A and time B and A and B, and we continue. Again, we compute the ID. This time the ID is a little bit larger, so that we will have this 64 unsigned integer. We generate this ID. We try to find it, and if we find it, we return it. Nothing else to do. So this is the memoization step. Now for the logic. It is a bit more complicated, but not so much. So we have this pending, this function just for simplicity that has pending. So pending means, is A or B pending? And what this means is that if the mask of opened, if we AND it with 1 shifted to the A position or 1 shifted to the B position, if this is 0, which means if bit A and bit B are 0, it means none of them are opened and thus both of them are pending. So if pending A be open means that these two nodes are pending. So what do we do? Again, we have a return value of 0 and we visit all neighbors. So if we are in A0, so if we are in the initial position, this is very similar to the other one. If we're in this position and we have pending both this neighbor and the other B, what we do is we try to solve traveling to this neighbor. So it is time A minus the distance, time B, the neighbor, B, and open. So this is similar to what we did before. The only thing we are checking here is if this is pending. This is a bit of an optimization. Here we were checking this in the beginning, if this is open. Here we're checking it before we do the call. So this is the initial case in which we are in the original position. So we want to move to neighbor I with the time of the distance without spending 1 minute opening this valve. Then the other case is a bit more complicated. This is helpful to make the search easier to have all these conditions. So the question is, if we are not in the initial position and we are not moving to the same neighbor, it doesn't make any sense to move to the same neighbor. So it doesn't make any sense to move from A to A again. And we don't want to visit B, because if we have the other agent already in B, we don't want to visit it either. And the time of A is larger than the distance plus 2. What does this mean? We want to go to neighbor I only if first, we can arrive there, and second, we have 1 minute to open the valve, and third, we have 1 minute to collect something from this valve. Otherwise, it doesn't make any sense. So this is a way of trimming the search. So we will only go to this neighbor if first the distance is, so we have enough time to get to the distance, get there through the distance. Second, have 1 minute to open it, and third, have 1 minute to release some pressure from the valve. Otherwise, we don't want to go there. And we also want to go there if this is pending. So if it is pending, both this neighbor and B and this to the opened, and we do this OR because that's what we are in A, then we do it. Why do we have to check this pending here? I mean, if we're in A and B, we already know it is pending, right? But it is useful because here we're swapping A and B, and there could be some kind of weirdness there. So we check that it is pending. If this is the case, then we visit it. And what does it mean to visit? Well, we do the maximum of the return value again, and we call solve2 with the time we have, -1, which is the time it took to open it. We subtract the distance, and then again, the time of B doesn't change. I is the neighbor, B is the other agent, and opened, we OR it with the A. So it means that we have opened A. Let's leave this for the end. And finally, what we return is we save in this memoization hash map the return value plus, and here we have moved it down here, the flow that we released from this agent A. So here we have opened A, so we remove it. Please note that here we open it, but here we don't open it, right? We said that we're not opening it if we are in the first valve. It doesn't matter because the first valve has flow 0, so this will be 0. Finally, there's one more case, which is this one here. So imagine we found out that we don't have anything to do. So that means that we could not travel from A to anywhere where we could get something, for example. But what if B is smaller than A, but B is able to visit somewhere? We will never find it because we have this swap in which we are swapping these two positions. So the solution is to call the first solve solution function from the first part of the problem. So the question is, from A, we could not visit anyone. So from A, we could not get any result. But can we from B? So we can just, again, do this call to the first problem in which we have a single agent, which is B, with this time B remaining, with this opened bit mask, and maybe B can get something. So this is the solution I came up with. It is pretty fast. It is interesting to find that you could find the solution with not such correct code. So there are some things that you could do here to improve the speed at the expense of reducing the search space to the point where this is wrong. So for example, here we say that the distance needs to be +2. We could put here a 5, which is clearly wrong. So we might skip some exploration, but maybe, yeah, we find the right solution in only 4 seconds. So what this does is it says, Vim 5. So what this does is we only move to a neighbor where we will have more than 5 minutes remaining. This is not really true. So if we put here a 5, we're not exploring all of the possible solutions. However, it makes the search faster. So it is important to know that in this kind of problems, you can trick yourself into doing some optimization that is really just reducing the search space. You still get the solution because we know this is the element of code and we know what is the correct solution, but that is not the correct way of solving the problem. I hope you enjoy it. Honestly, I didn't check any other solution from anyone else, so I don't know if there is a simple way to get a solution to this problem in 1 second. I don't know. I just iterated over with my code and ended up finding this. I hope you enjoy it. See you some other time.